Hello, I hope you are doing well and ready to explore solids with me. We're looking at 11.5. Our essential question is, how do I identify solids? You may notice that the objective, I actually made a mistake there, so cross out polygons and put solids. So the question is, how do I identify solids? So when we talk about solids, we're talking about these three-dimensional objects is what we're doing now. Everything up to this point has been two-dimensional. Now we're getting into 3D. And a polyhedron is a solid that is bounded by polygons. So polyhedron, we're familiar with that prefix of poly, that's many. Hedron is a word that can mean face. So polyhedron has many faces to it. And so again, a polyhedron is a solid, a three-dimensional object that is bounded by polygons. Let's remind ourselves what polygons are. They are a closed figure with straight sides. Polygon has straight sides to it. And those polygons that are binding up this polyhedron are called faces. So here's a polyhedron, and you can see it has a face here, the surface to the three-dimensional object. And it encloses a single region of space. In other words, there's not any openings to this polyhedron. So there's different aspects of this polyhedron. Like we said, this is a face, this flat surface here. An edge is a line, a straight edge, you would call it. That's a line segment formed by the intersection of two faces coming together. And then a vertex, we are familiar with that, but we're accustomed to it in two-dimensional, where it's only two lines that connect together to create a vertex. But in three-dimensional, there are three or more edges that meet together to create a vertex. So that's the definition of a polyhedron. The plural of polyhedron is polyhedra or polyhedrons, but we're going to use the term polyhedra typically. So there are 5 different solids that we are exploring that we need to begin to become familiar with. On the left-hand side, you see these are polyhedra. This is a polyhedron, and this is also a polyhedron. Because there's more than one, they are polyhedra. And on the right side, these are not polyhedra. So why is that the case? Well, remember we said a polyhedron is bounded by polygons. So you can see for this prism that each of these sides, or each of these faces, are polygons. And same thing here with the pyramid. Each of these faces are polygons. Whereas for a cylinder, this side here, going all the way around, is not a face. That is not a polygon. It's not a closed figure with straight sides. See how this is curving around? So that is not a polyhedron. And same thing with a cone. Also, that first of all, a circle is not a polygon, and then also the cone is not a polygon. And of course, with a sphere, a basketball basically, or a ball, that is not a polyhedron. So let's also make some other connections with these. I'd like for you to connect prism and pyramid. Prism and cylinder. Let's do that first. Prism and cylinder together. Because notice that a prism has actually 2 bases to it. Maybe we can look at the pyramid first of all, and obviously there's one base to this pyramid that it is sitting on. It's even more obvious with a cone. There's only one surface that you could sit this thing on. So both the pyramid and the cone have one base, whereas the prism and the cylinder have two bases. And in order for them to have two bases, those two bases have to be congruent, meaning that this face on the bottom, this face on the top have to be congruent with each other, and also have to be parallel with each other, or existing in parallel planes. So you see that's the case with the prism. It's also the case with the cylinder. We're really going to need that definition, that understanding of the connection between prism and cylinders, as both of these have two bases, and a pyramid and a cone only have one base when we look into volume and surface area in the next sections coming up. Let's look in the book here about classifying solids. This is a prism because we have two bases. These bases are parallel to each other and they're also congruent. And what kind of a base is it? These bases are pentagons, and therefore we would call it a pentagonal prism. And here's a pyramid. You see it only has one base, and this particular pyramid has a triangle as its base, and therefore we call it a triangular pyramid. So pyramid is the noun, triangular is the adjective that modifies your noun because it's describing the kind of the shape of the base of that solid. Example number one. Let's understand. Oh, you know what? No, we did talk about it, right? Yeah, we did talk about back here the vertex. If you could make sure to draw this little line, these little arrows, identify the vertex is this intersection of the three or more edges. Edge, of course, is this straight line here. And then if you would also, in your notes, if you would identify these capital B's here for bases, and also write in that both the prism and cylinder have two bases that are congruent and parallel, whereas the pyramid and cone have only one base. And tell you what, let me also identify, point something out to you that I have written here, that notice on a prism that a prism has rectangular sides. So these, think of it this way, look at this three-dimensional, this is a prism. Notice that each of these sides here for the prism are rectangular. Whereas for a pyramid, you might say, okay, what is it that makes a pyramid unique? Well, a pyramid has a point. Oh, yeah, it does have a point. You got a point there. But the prism also has points. So what is it that makes a pyramid unique from a prism? And it's the fact that the sides for a pyramid are triangles. So notice on this pyramid that each of these sides are triangles, and they all these triangles come together into this one unique point that's opposite of the base, and that point is called the apex. So there is no apex here on my prism, where all the triangular sides come together at one place. And for a cone, it's easier to identify. The apex is right up there. It's not hard to do. Okay, so example number one. They're asking us to tell whether or not the thing is a polyhedron, and then if it is, to name it, and then to find the number of faces, vertices, and edges. So is this a polyhedron? And the answer, remember, in order to be a polyhedron, it needs to have two bases, and those bases need to be congruent and parallel. And that is the case here. Here's a lower base and an upper base, and they're congruent, and we can assume that they are parallel because we have all these congruent markings there. If we didn't have those congruent markings, it might look like it's a polyhedron, but we cannot prove that it is. So how many faces does this thing have? What I typically do is, once you identify it's a prism, so you know it has a top and bottom, 2 bases to it, and then count the number of sides. And there are 4 sides added to the 2 bases. That makes a total of 5, what am I saying, 6 faces. And vertices, what you can do is look at one of these bases and see there are 4 vertices on this lower base, and there's also 4 vertices up on the upper base. So 4 plus 4 gives us a total of 8 vertices. And edges, that's a little bit harder. Here for your base there are 4 edges. The upper base also has 4 edges, but then notice that the sides of this polyhedron, this prism, also have an additional 4 edges to it. So 4 plus 4 plus 4 gives us a total of 12 different edges on this prism. This guy here, is this guy a polyhedron? Remember, to be a polyhedron, all the sides have to be polygons, and polygons are straight sides to it. And so yes, this is a triangle, and this is a 1, 2, 3, 4, 5, 6, so that's a hexagon, and all these other around here are also triangles. So yes, this is a polyhedron, and because it has 1 base and has triangular sides that all come up into this one point, that's called an apex. Therefore this guy is a pyramid. And I'm not going to go through counting, well, let's count faces, I guess. So faces, there's 6 sides on your base, therefore there's going to be, or 6 sides to the base, therefore there's going to be 6 faces around this polygon. And there's also the base is another face. So the base is a special kind of face, so it is considered to be a face. So in this case there are 7 faces in this pyramid, and vertices, there are the 6 going around here, and then just the 1 apex, which is also a vertice, so that would be 7 vertices. And then edges, there are 6 going around, and also 6 on the base, so that would make 12, if I'm correct. Yep, 12 edges. Now this dude, is this guy a polyhedron? To be a polyhedron, it needs to be enclosed by polygons. And wait a second, this is a circle, that's not a polygon, and therefore no, this is not a polyhedron. It's a cone, like this, and has only 1 base to it, and the other end here is a apex. So now you're ready to go through this guided practice that you have in your notes. These 3 problems down here, naming the polyhedron, or whether or not it's a polyhedron, and what kind of polyhedron it is, if it is, and the number of the faces, vertices, and edges. Let me go back to this one. So yes, this is a prism, but what kind of a prism? It's a rectangular prism. And yes, this is a pyramid, but what kind of pyramid? It's a hexagonal. Hexagonal, there it is. A hexagonal pyramid, because it has a hexagon as its base. So go ahead and pause the video and do your guided practice on your notes. Let's look now at Eulers Theorem. This Euler dude, Leonhard Euler, was in the mid-1700s. He was playing around with polyhedrons and realized that there is a relationship. And I have it on your notes here on the back. There's a relationship between the faces, vertices, and edges of a polyhedron. And so let's call the faces F, the number of faces F, the number of vertices V, the number of edges E, and Euler, that's how you pronounce his name, is notice that F plus V always equals E plus 2. for polyhedrons. So let me show you an example of that. I actually think this is a pretty lousy example because it's confusing with the beams here. You're wondering, okay, are those edges or not? But it's not. We're talking about the solid. So just look at the outside post here on this this house, and if you were to count up the faces, there's a base here, and actually this is a prism, but this would be your base to the left side, and this is your base on the right side, because these two faces on the left and on the right are parallel and congruent to each other. And then notice that there's 1, 2, 3, 4, 5 sides around this house, including the floor would be one side. So there are 7 faces, and then vertices. If you count the number of vertices, there are 5 on the left side. There's 5 on the right side. That would add up to 10. So there are 10 vertices. And then edges, if you could go through and count all the edges, but since we know Eulers' theorem, we can calculate the number of edges. So we plug in the number of faces, the number of vertices, and then solve this equation for the number of edges. So we'd add 7 plus 10 is 17, and then subtract 2 from both sides, and so there are 15 edges. So there's 5 on this side, 5 on the other side, and then 5 that are connecting those two sides, so it makes a total of 15 edges. Let's look now at the definition of regular polyhedra, and I did not put that in your notes, so let me have you write that in if you would. Regular polygon. Again, polyhedra, I guess I shouldn't put polygon, should I? Yeah, I need to put, I guess you could say polyhedra. That's plural. So let's not do that though. Let's do polyhedron. Let's write that, because I did it as a singular. So if you would write in your notes, regular polyhedron. And what is a regular polyhedron? It's a polyhedron where all the faces are congruent regular polygons. All the faces are regular congruent polygons. And let me show you examples of that here in your book. And it turns out that there are only 1, 2, 3, 4, 5 regular polyhedrons, and polyhedra, I should say. And they call those 5 regular polyhedra Platonic solids. That's just a special name. I guess the philosopher Plato emphasized those regular polyhedra, so they call them Platonic solids. So regular polyhedra and Platonic solids are essentially synonymous, because there's only 5 Platonic solids. And I won't get into all the details here. One more term, though, would be helpful for us, is convex. You'll remember that a convex polygon is where it bends in, where one of the vertices is pointing in on your polygon. Same concept. I'm sorry, that's concave, isn't it? I got that mixed up. I thought I did that. So I'm creating a cave by pushing that in. So that's concave. Convex would be if all the vertices are pointing out. So same concept here, that here a three-dimensional object, a solid, if it's poked in, let's give a non-technical definition to that. If it's poked in, it is concave, and it is not convex. That's pretty intuitive once you are familiar with those terms. Example number 3 in your book. Yep. Let's use Eulers' theorem on this Platonic solid, and if we counted up all the faces, there are 8 faces on here. you can see if I was to cut this thing in half, it'd be like a pyramid, but it's two pyramids together, so it's not a pyramid, but it's just a polyhedron. And if I was to count the faces, I'd have 4 on top and 4 underneath. That makes a total of 8. Vertices, there are 4 around the sides and 1 on top and 1 below, so that makes 6. And then edges, there are 4 around the top and 4 around the bottom, and also 4 around the sides. Makes a total of 12. So what they're doing here is just confirming Eulers' theorem by counting up the number of faces, vertices, and edges, and then plug it into this formula to see if it indeed is true. And so go ahead and stop the video now and do these 6 problems here. And if you would, do it by putting, like I have here, the number of faces. So count up the number of faces and put that number there. Count up the number of vertices, put that number there, and count the number of edges on this polyhedron. And then write the formula to remind you of what that formula is, and then plug those 3 numbers into your formula and see if that confirms and works in this formula. So for each of these, it should work. Each of these are polyhedrons, and so Euler's formula or Euler's theorem should be true for each of these 6. Last topic now is to talk about cross sections. Let's look at that in your notes. Cross sections. In fact, let me highlight that here. And it really is easier to see it with the coloring. So let me see if I can. Nope, can't. So think of it as you have a 3-dimensional solid, and basically take a saw and cut that solid somewhere across the solid, and that's going to create a cross section of that solid. So for example, well here you can see that we have a pyramid, and then this plane, you can think of that as a saw cutting off the top of this pyramid, and this cross section, you can see in this case the cross section is a triangle, and it appears as if this saw that we're bringing in, this plane, is parallel to the base. So the base was a triangle, and in this case the cross section is also a triangle. Let me show you some other shapes here. If I was to have a cube, this is a prism. Could be a rectangular prism, or it definitely is a rectangular prism, but could be a cube, which is essentially a square prism, where all the faces are squares. And if I was to cut that straight parallel with its base, it would make another square there. If I was to use that same cube, though, and instead cut it at a diagonal, notice that I'm not creating a square, but instead, this case, I'm creating a rectangle. So the cross section in this perspective is a rectangle. And then using the same cube, if I was to cut it at an angle, as you see here, it would actually create a trapezoid, wouldn't it? Because this top part, these two are parallel, top and bottom are parallel, and the top is longer than the bottom, and so that is a trapezoid. So using different cross sections of a cube, you can create different shapes. Here's an example, if you can see that, of taking a cone, and if I was to come in and do a cross section on this cone, I could cut off the top here, and what would that create? In this case, it creates an oval because it's at an angle. If it was parallel to the base, it would create a circle, but at an angle, it's creating an oval. Alright, so that is it. You are ready now to finish these last three. These do not come from the book. In order to make it stand out and be clear, use this black and white version. And what it's saying is here is your cross-section plane, and where it is traced on the polyhedron is where that plane intersects your solid. So this is with the intersection here that it's creating. That's your cross section, and then here it's kind of like a sausage or a cylinder, and you're cutting it at an angle. And right here is where this cross-sectional plane intersects with that cylinder. And I think this one you can kind of intuitive. You can see that here's your plane, and it's creating this cross-section there. Okay, hope that's helpful, and I look forward to seeing you in class soon.